Chapter 6, Flooding. Welcome back. Climate change will affect both the frequency and magnitude of flooding as components of the hydrologic cycle are altered. Some areas may get less precipitation, but all at once, while other areas could get more total precipitation. Both scenarios can lead to flooding. 6.1, An Introduction to Rivers. Streams and rivers are part of the hydrologic cycle. Can you see them? They can be fed directly from rain, or perhaps the precipitation stays as snow and/or ice for a while before melting and feeding streams and rivers. The precipitation could also be stored in the ground as groundwater for a while before the water works its way to the surface and forms a spring that feeds a stream. The stream can feed a lake, and then the lake can feed another stream. There, all those streams and rivers carving and depositing much of our landscape. Runoff, which is the surface drainage that quickly coalesces into streams, which forms the tributaries of rivers. This combination of surface runoff to streams to rivers covers an area known as a drainage basin. Other words for drainage basin include watershed, river basin, or catchment. River basin usually refers to a larger area than watershed or catchment, but have the same meaning. A drainage basin is delineated by a drainage divide. If a drop of water fell on the inside of the drainage divide depicted in these images, it would eventually feed the river in the image. If the raindrop fell on the other side of the drainage divide, the water would feed into a different river system. All three images show drainage basins, drainage divides, smaller tributaries, and larger rivers or streams. The river may end in a lake or the ocean, or even another larger river. This ending point is the base level. The ultimate base level is the ocean. A river gradient is the slope of the river. The image to the right shows the longitudinal profile of a stream. Along the x-axis is distance, and along the y-axis is elevation. Notice the general pattern of the curve. At first it is steep near the headwaters, and then gradually becomes less steep as it approaches a base level, with the ultimate base level being the ocean. This general pattern is an exponentially decreasing curve. The image on the left gives you an idea of what the 2D graph looks like in 3D. The headwaters are higher elevation, often in mountains where it is steep, and then the foothills, which are less steep. Then onto the plains, which have more of a gentle slope, and then finally a base level. The slope corresponds to amount of energy of the stream, which corresponds to type of sediment deposited. The steeper the gradient, the faster the stream will flow. I hope that is not news to you. Streams flow faster when the slope is steeper. The faster the stream goes, the more sediment and the larger sediment it can carry. So what we see on the stream bed are slightly larger rocks, because all the smaller rocks, sand, silt, clay, and dirt, are washed away, carried downstream. This image is again a longitudinal profile of the stream. Distance is along the x-axis and elevation is along the y-axis. The scale is relative, and so it's not marked in numbers. This could be a super long river or a short stream. Given enough time, all rivers and streams look like this. Starting on the far right at the headwaters, high gradient, high energy. All the small stuff is washed downstream. So what we see on the stream bed is coarse gravel. Go up even higher, and the stream bed may be strewn with cobbles or even boulders. This is a mountain stream. You can picture when Can you picture one you've seen? Do you see the water jumping around, possibly even forming some rapids? This jumping, splashing water is indicative of turbulent flow. Go a little further downstream. Moderate gradient, corresponding to moderate energy. So it can't carry as big of pieces of sediment as it did closer to the headwaters. Coarse sand is deposited here. The stream just doesn't have the energy to carry it further downstream. Fine sand, silt, clay, and dirt are washed further downstream. Now we enter the plains. Low gradient, low energy. Flow becomes more laminar, less turbulent. Gone are the splashing streams of the headwaters. Here are the lazy streams, with a clear channel where water and whatever else is in it flows fairly smoothly. Though the stream may have substantial flow, its energy is low, and sand and silt settle out on the stream bed. Follow the stream even further, and it enters its base level. Here the water almost stops. The energy is so low it can't even carry the finest of the fines, clay-sized particles. And so here, at last, the clay-sized particles are deposited. If you walked here, you'd be walking in muddy gunk. Okay, so you might be thinking, well, I know places with high elevation that have fine sand deposits. But in general, what does the stream generally have on its bed? Does it have fine sand deposits all over, or just in a few point bars? Does it have fine sand there all year, or does it build up as high water recedes each year? And the stream begins to slow down. Also, a high elevation stream can have a high elevation lake or dam that becomes a temporary base level. And so you can also find muddy gunk to wade through even in the mountains. And remember, streams approach this longitudinal profile as it weathers and erodes the landscape over time. And I'm talking geologic time. And so like many, many thousands of years, to even many millions of years. Some landscapes are still fairly young, geologically. Also, the general cross-sectional geometry of streams changes as you go from the headwaters to the base level. Upstream, closer to the headwaters, the cross-section of the stream is generally smaller and more V-shaped, as it carved into the rock by the fast-moving stream. See figure B. Much of the sediment is carried downstream. In contrast, downstream on the plains, the stream valleys are much broader. See figure C. The stream channel is carved into sediment that has been deposited on the floodplain. So what's a floodplain, you might ask? It is a relatively flat area next to the stream, filled with stream deposits such as sand and gravel. This flat area has been produced by the river as it meanders and as it floods. Can you see the floodplains in these pictures? The cartoon is easy, it's labeled. But how about in the picture? You see the meandering stream channel, kind of like a giant black snake slithering through the valley. There's some white stuff. I'm guessing snow or sand. And then there are trees on the slopes. The floodplain extends between the tree-covered slopes. Did you see it? Can you see it? If not, check out your book figures too. Materials transported by rivers. Rivers transport materials along with water. We will identify three types of loads: dissolved load, suspended load, and bed load. Okay, so imagine wading in a stream or a river. What you're walking on in the stream is the bed load. This load is made up of sediment that the stream does not have enough energy to wash away. The stream energy may bounce or roll the bed load along the bed of the stream, but will not substantially move the bed load downstream until it gets more energy, such as perhaps during a flood. If we are in a rushing mountain stream, what might the bed load consist of? Did you say cobbles? Coarse gravel? Right. If we are in a lazy stream on a wide plain, what might the bed load consist of? Did you say sand or silt? Right. And we know why too, right? Stream gradient, relating to velocity or energy of the stream, which relates to what the stream can carry and wash away. So the washing away load is called the suspended load. When you are wading in a stream, this is what hits your legs. In a rushing mountain stream, the suspended load might be sand and silt. Your legs could be getting sand blasted. In a lazy-daisy stream on a plain, the suspended load might be clay-sized sediment that you might not even notice until you really try to see it. This is the sediment that the stream has enough energy to wash away. This sediment will all eventually get deposited as the water loses more and more energy and becomes more and more still. The last load we'll discuss is the dissolved load. This load you cannot see or feel. It is composed of ions in the water. These ions are throughout the water column, from the bed of the stream to the surface. These ions have charges, plus or minus, which the polar water molecules dissolves. So you cannot see or feel these ions. They are throughout the water column. How do you know that they're there? You can trust me, or you can taste the water. What you taste are the ions, the dissolved load. Another evidence for the dissolved load is hard water. Do you have it? Does it make your toilets hard to clean and coat your shower with a film of hard stuff? This is the dissolved load precipitating in your home. It is generally calcium and magnesium carbonates. When dissolved, the calcium and magnesium are positive ions, cations, and the carbonates are negative ions, anions. And together they form rock, which we like as limestone and cave formations, but do not quite appreciate as hard water stains. Dissolved load. When it's dissolved, you cannot see it or feel it, and it is throughout the stream, but you can taste it.